Hello, Precalc students. We are moving on in our probability distributions unit. So we are in unit 3, and this is now going to be a little explanation of lesson 4, which is about normal probability distributions. So what are we going to do today in this lesson? Well, calculate the probability that a normal random variable x falls below a value, above a value, or between two values, and we're going to use our calculator to do that. Well, we might not use our calculator as well, but for the majority of it, we'll use our calculator. We are going to calculate a value of a random variable given the area under a curve, which is inverse norm. This one up here was normal CDF or PDF. This is inverse norm. And then we're going to transfer a normal random variable x into a standard normal random variable z. So you might look at your theorem sheet, or not theorem sheet, sorry, that's geometry. Look at your formula sheet and notice that we have a z-score or a z formula on your formula sheet. So that's what we're referring to when we talk about the random variable z. Normal probability distributions. It says normal probability distribution is a continuous distribution that arises in many natural processes. So continuous, what does that mean? Well, it means between any two data values, we could, at least in theory, find another data value. So a lot of examples are around weights or heights or circumferences of like your head when you're a baby. So remember, if you ever look at like when a baby is born, parents want to know, is my baby normal? So they want to see, where are they on the charts? How does their weight compare to other babies around the world or in their region of the world? Or how is their head circumference? What does that mean? Is it too big? Is it too small? How long are they? So all these different things we find out. In this example here, we talk about oranges. Oranges picked from a tree. So will all of the oranges have the exact same weight? No, they're going to vary. They're going to vary based on a lot of things. They're going to vary based on their genetics, how much time they had in the sunshine. Was their conditions of the weather good? Did it rain a lot? Did it rain too much? Was there a lot of wind? Were the orange trees fertilized or not? So yeah, so there's lots going on there that's going to have an impact on the weights. So every single weight is not going to be the same. However, we will find that they will fall into a bell-shaped distribution. So a random variable x whose distribution has the shape of a bell curve is called a normal random variable. So oranges would be, the weights of oranges, I should say, would take on the shape of a bell curve. So in the middle of our bell curve right here, so this is our bell curve going around. In the middle of the bell curve is always representative of your mean, and we use this mu for mean. And then these little marks right here are representing standard deviations. So this is 1 standard deviation away from the mean, 2 standard deviations away from the mean, 3 standard deviations away from the mean. If you go to the left, then you indicate you're going to the left of the mean, so smaller than the average. That means that you'd be -1 standard deviation away from the mean, 2 standard deviations, but you're going in the opposite direction where values are getting smaller, so we put negatives there. Okay, so I just threw out the word standard deviation. I think all of you know what mean is, the average, but what does standard deviation represent, or mean? So standard deviation says the standard deviation measures the spread of the distribution. The more spread out the data is, the greater the standard deviation. So the larger the standard deviation is. A standard deviation close to 0 indicates the data points tend to be close to the mean. So we have a little example over here. I'm going to kind of toggle between this example and this one here to talk about what these values are and what the heights, why they're look a little bit narrower and skinnier through here versus spread out a little bit more. So it says in a normal distribution, approximately 68%. So 68%, you can see that's indicated here. 68% of the data falls within 1 standard deviation of the mean. So 1 standard deviation to the right of the mean, 1 standard deviation to the left of the mean. So it looks to me like here it's saying that the average is equal to 60. And if we go to the right 5 units to get to our first, this is 1 standard deviation away, then that means my standard deviation is 5 units. So 65 to the right and then 55 to the left. So I'm adding 5 to the average to get 1 standard deviation away, and I'm subtracting 5 from the average to get 1 standard deviation away. So 68% of the data is 1 standard deviation away from the mean. Then it says approximately 95% of the data falls within 2 standard deviations away from the mean. So if I add the standard deviation of 5 twice, I get here to 70, and then subtract it twice, I get to 50. So 95% of the data falls between 50 and 70, which is 2 standard deviations away from the mean. And then here it finally says 99.7% of the data usually lies within 3 standard deviations of the mean, which means we have a very small portion here in the end, right? This itty bitty bit here, this itty bitty bit here, that's only 0.3% according to this the standard normal curve. So if you look up here, right, we have an average of 100, and this number right here is 150. So if we had a standard deviation of 10, we would go to the right 10 and to the left 10. So this is 110 and 90. So this is 1 standard deviation away. So 68% of the data is between 90 and 110. So if we go 2 standard deviations away, that's 120 and 80, then 95% of the data needs to be between these 2 standard deviations. So you can see this really large, this curve right here is representing when you have a small standard deviation. Then the data has to be a lot closer to the average. So the larger the standard deviation, like this one, the more spread out, right? Then it goes to 20, 120, and 80, so it's 1 standard deviation away. And then we go 140 and 60 is 2 standard deviations away, so it's more spread out. So once we establish our model, we can use it to make predictions. So that's when you're born, babies are born, and they say, oh, your baby compares to the rest of the babies that we've collected data on in this way, and it tells you, where you lie in comparison to other people. So here's some important properties of a normal distribution. Number 1, it says the normal curve is symmetrical about the mean. So if this is your average right in the middle, you can see that you have perfect symmetry on the right-hand side over here and on the left-hand side. So if you folded the paper down the mean, you're going to get the exact same picture on the right and left. The mean is at the middle and divides the area into 2 halves. So we have this half over here, which is representing 50% of the information. Oh, that 50 looks weird. And we have the half on the left-hand side over here, which represents 50% of the information. So each side to the right of the mean and to the left of the mean represents 50% of the information because it divides the area into 2 halves. The total area under the curve is 1. Right, so this is 0.5, this is 0.5, so the whole entire total area under the curve is equal to 1, or 100% of the data should be underneath the curve. And the mean together with the standard deviation define the shape of the bell curve, right? So what is the mean, what number goes here, and then what is the standard deviation, how big is it, how far away is the data spread apart? So that information is establishing what the shape of the curve looks like. So let's look at this example number 1. It says the random variable x is normally distributed with a mean of 15. So we have this mean right here in the middle of our bell curve. It says let R be the shaded region under the curve to the left of 17. The area for R is 0.71. So all of the shaded purple area that's on my paper, this has a value of 71% of the data is from 17 and below, right? And what does that mean then about this area over here? Well, that's actually question letter A. What is the probability that x is greater than 17? If the probability that x is less than 17 is 0.71, and you know the area under the curve is equal to 1, right? So what percentage of the data will be over here above 17? Well, hopefully you're just saying that's 1 minus 0.71 So 29% of the data, or 0.29, is what the probability that whatever this data is representing, there'd be a 29% chance that the value would be greater than 17. Okay, how about for the value to be caught between 15 and 17? So what is the area of this red portion of the graph? Well, remember that the mean, which is 15, separates each side into having 50% of the data here and 50% of the data of the entire thing on the right-hand side. But we just said the yellow portion is 0.29. And if this entire right-hand side that I'm outlining in black is 50%, then hopefully you're saying, okay, well, I have to subtract 0.29 from 0.5, or 50% minus 29%. And so that would be 21% of the data is represented by this red portion right here. And finally, let's look at our last example. It says, what is the probability that the values of x are caught between 13 and 17? So 13 is where and 17 is where? Well, we just saw that 17, we then know that this information right here, the red part, is 0.21. So from the average 15 to 17 is 0.21. So now I'm going to add that to 13 plus, the area here between 13 and 15. Well, what do you notice? 15 goes to 14 goes to 13, that's 2 standard deviations away potentially, and then 16 and 17, that's 2 standard deviations away. So these two sides are equal to each other. So actually it's just twice 0.21, right? So you could have just written this down, or you could have just said that's 42% or 0.42. I would leave your answers as decimals because remember you always have to write to 3 decimal places. And so when you get more complex numbers that are more than just these 2 decimal places, you might want to just leave it as decimal so you don't have to round and have a 42% and then 42 point blah 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 and have 3 more decimal places there. So just leave your answer as decimals instead of having percentage answers. But it's up to you, we'll accept both, but you need to have the numerical values that go on further rounded to 3 decimal places or more. Okay, if you don't have your calculator nearby, then you should probably pause right now and grab your calculator because these 3 questions we're going to use the calculator in order to solve. I'm not going to be able to show you my calculator screen, but if you look here on the right-hand side, I'll tell you what buttons to push, and then you should be filling in what you see here on the right-hand screen and trying to get the answers that I'll show you and show you the work that you should have on your paper as well. So example 2 says, in 1999, the heights of rugby players were found to be normally distributed with a mean of 179 centimeters and a standard deviation of 7 centimeters. Okay, so let's put that on the spell curve right now. So if you're a visual learner, we're trying to show you visually what that means. So right here in the center is your average, and our average is 179 centimeters. I'm not going to write the centimeters because I just don't have space. So if the standard deviation is 7 centimeters, then 1 standard deviation away is going to be 179 plus 7, which is 186. And then 1 standard deviation away to the left-hand side is 179 minus 7, which is 172. So remember going back earlier in our notes, that 64 or 68% of our data is in between your first standard deviations. And those should be exactly mirrored equal distances there. This area should be the same. So I'm a little bit off, but that's okay. So this gives you an idea, if you kind of draw it out and you say, okay, well, what's the probability that a randomly selected player in 1999 was less than 175 meters tall? Well, where is 175? It's here somewhere. It's closer to the 172 than the 179. And so this would be my 175 right there, and it says less than. So what I'm trying to do is calculate the area under the curve for the number where it's 175 here on my grid. So this is a 175. So I'm trying to calculate this area under the curve right here. Okay, well, how do I do that? I have to use my calculator, and I have to use something called normal CDF. CDF meaning we're having cumulative. I think we talked about this in binomial probability. You have cumulative, you have more than one. You have to go and find a bunch of area under the curve between two different numbers. So go to your calculator, push the menu button, and you're going to go to your probability or your statistics. If I go to probability, then I go to number 5, distributions, and then you look for your normal CDF. Push your normal CDF, and then it's going to say lower bound. You can put negative, mine says negative 9E9999, that's fine because that just means negative point or negative 9999. You can type in negative 99999 or negative 1000000. So you want a huge negative number because it's going to go on infinitely here. Then your upper bound is where you're stopping. So we're stopping at 175. So this is my lower bound, negative 1 million or whatever you want to put in there. Negative infinity is fine. Your upper bound is 175. Then they want to know what is the average, which is 179, and what is the standard deviation, which is 7. So the work that you would have to show on your paper is when you put those values in, it's going to spit out normal CDF and negative infinity, 175, 179, and then 7. So this is the work, because this is what it's going to spit out on your calculator. And then your answer. So you're going to get a method mark for having that written on your paper, showing us what you plugged into your calculator. And then you need to have your at least 3 decimal places. Usually we just go to 4 in our answer keys. Sometimes we round to 3, but you should have gotten 28% roughly, or 0.2839. So 28% or 28.39% of the rugby players are going to have a height that is less than 175 centimeters tall. Okay, moving on. So if you want to keep drawing this, you can. So 179 here is in the middle, and I'm going to go from 170 to 190. So it says, what is the probability that a randomly selected rugby player in 1999 was between 170 and 190 centimeters tall? Well, 172 and 186 were 1 standard deviation away, so we're going a little bit beyond the 1 standard deviation away. So we use our calculator, normal CDF. Our lower bound this time is 170. Our upper bound is 190. Our average is 179, and our standard deviation is 7. So we have normal CDF. This time lower bound, upper bound, right? So you would write this on your paper, and when you plug that into your calculator, it should have spit out 0.8427. So roughly 84% of rugby players in 1999 had a height between 170 and 190 centimeters tall. And those are not equally distributed here, sorry. So 170 would have been a little closer. If I'm really going to visually draw this, it would have been a little closer over here and a bigger area over here on the right-hand side. Okay, now part B is slightly different. We're going to use a different function on our calculator to figure this one out. So what happens when they give us the actual, sorry, I don't know what I did to my computer screen here. Sorry, I had to pause there and figure out what button I pushed. Sorry about that. So now what happens, this time we're telling you we have to actually find the height. So, oh dear, what am I doing? Okay, so we have to find the height of when we will get 80th, what's the 80th percentile? So what height is that? So we know we have 179 centimeters here in the middle. And we know from earlier in the information that you went from the center out, so like 68% of the data was from here to here, and then 95 went out from here to here, and then 99.7, etc. But the 80th percentile is just going to be some number, some spot over here. So the 80th, we have 50% to the left. So when it's talking about the 80th percentile, we're going from the left until we get to where 80% of the information or of the data results are the area under the curve right here. So I'm trying to figure out what height is associated with this right-hand value right here, where to the left of that would be 80% of all of the data. So when we give you the percentile, you have to use something called inverse norm or inverse normal. When you go to your calculator, and you go to menu, and you go to your probability, and you push your distributions, you will see something called inverse normal. On mine, it's number 3. And so it says inverse normal, and when you push that, it says, then you're gonna put in your area, right? So your area is 0.8, so you put in 0.8. Then it tells you to put in your average. Your average is 179. And then it says to put in your standard deviation, so your standard deviation is 7. So when you do that and you push enter, you should have gotten that you would have 184.891. So that means for rugby players, 80% of the rugby players in 1999 were at a height of 184.891 centimeters or below. So that is what that information tells you. So when we give you the percent, you're doing the inverse. You actually have to find the height. So remember, that's the opposite, right? Inverse. So we're inverse normalizing this. So you go plug that in, plug in the information, and get your answer. Okay, so this next page, I kind of went over and I'm trying to put these examples over here in the context of what we were just talking about. So now we're going to talk about standard normal distribution. So the standard normal distribution has a mean equal to 0. So right here, our mean is equal to 0, and then a standard deviation of 1 unit. So then 1 unit to the right would be positive 1, 1 unit to the left would be negative 1. So in real-world applications, it's sometimes necessary to standardize the normal distribution so that the calculator functions such as inverse norm can be used in the context of the problem. And we'll see that as the very next example that we do. So in order to normalize this data, we're going to use something called the z-score, and the z-score is on that yellow sheet, on your formula sheet. So you can use that on your test. So you don't have to memorize this, although it might be instinctive to you. It might make sense as you start to use it. Okay, so we had our previous example with the rugby people, the men in 1999, and their heights. So the average for their heights was 179, right? And then the standard deviation was 7 centimeters. So 1 standard deviation away, which I used red here, is 186. So 1 standard deviation away to the left, and 1 standard deviation away to the right was 186, to the left is 172. So if I want to normalize that, then here, right, the 186, the 0 is representing my average right here. That's my average. 1 standard deviation away would be equivalent to where the 186 is located on that standard normal curve above, and then 1 standard deviation away to the left, which we represent by -1, would represent where 172 is represented for our heights. Now, if we had a height of 175 and we wanted to know, well, how many standard deviations away is the height 175? Well, how would you calculate that? Right, so we're trying to figure out what is this distance. If from 179 to 172 is a distance of 1 standard deviation, then what is it from 179 to 175? So we have our z-score to calculate. So down here is where we are actually calculating our z-score. So this says, in order to calculate our z-score, we're going to take the value of x, which in this case is 175, That's the score we're trying to attribute to a z-score down here. We're going to subtract the average from it, which is 179, and we're going to divide by the standard deviation. So if 1 unit away is 7, right, 1 standard deviation away is 7 centimeters, then I would take this difference, right, 175 minus 179, the difference, and divide it by 7. That shouldn't be a negative there, sorry. Divide by 7. So take your calculator, 4 divided by 7, what do you get? And we get 0.57143, so 175 centimeters is roughly 0.5714 standard deviations away. So it's not quite half a standard deviation away, isn't 0.6 of a standard deviation away. It is 0.5714 standard deviations away, and it's negative because it's to the left of the average. So that's how we would use our z-score. Or I'm sorry, that is how we would calculate the z-score. We will see why we need the z-score in a future example. So here, if we did the same thing with this 190, if we're trying to find a z-score that is associated with 190, well, again, our z-score is equal to, we take this value that we're trying to attribute to a z-score, like to find how many standard deviations away it is from the mean, right? So we're trying to figure out how far away from the mean, how many standard deviations away from the mean 190 is. So we do 190 minus 179, and we divide by the standard deviation of 7, so that would be 11/7, and if you plug that into your calculator, you would say that 190 is roughly 1.5714, so it's about it's more than 1.5 standard deviations away. It's less than 1.6 standard deviations away. It's specifically 1.5714 standard deviations away. All right, so why do we need to know this information? Let's find out. Okay, our cookie factory problem, hope you're not hungry. It says, in a cookie factory, the mass of Oreo cookies is normally distributed with a mean of mu and a standard deviation of 1.5 grams. So once again, we don't know what our average is, or our mean. For part A, it says the probability that a cookie has a mass less than 42.5 grams is 0.9522. So there's roughly a 95% chance that any cookie made will have a mass less than 42.5 grams. So how do we use that information to help us find the average or find the mean? Well, they gave us the area under the curve. And as soon as you see that the area under the curve was given, right, so here's 42.5, and I put it over here to the right of the mean because I know I have a large curve, or a large area, sorry, that was given, and I go from the left all the way over here until I get to 42.5. And I know from the left-hand side to the average is just going to be 50% of the data, so it has to go beyond that, so I have to be 45.4522 beyond the mean. So that's why I put the 42.5 over to the right like that. So every time they give you an area under a curve, you need to use inverse norm, right? That's going to be where you want to think to start. So the area under the curve is 0.9522, so go to your menu button, go to your probability, go to your distributions, choose inverse normal, and now put in the information that you know. So we know that there's an area under the curve that's 0.9522. And now I'm going to normalize it. I don't know the average. I don't know the mean. So I have to put 0 as my mean with 1 as a standard deviation away. So it can give me how many standard deviations away 42.5 grams is from the mean. In other words, we just calculated our z-score, right? So this means that 42.5 is 1.6666, etc. Standard deviations away from the average. Now I can use my z-score of 1.6666 to calculate the average. So look at your z-score formula. You take x, which in this case is 42.5. You subtract the average, which we don't know, the mean, mu, and we divide it by the standard deviation, which was given to us in the beginning part of the problem. So you cross multiply, do your algebra, solve. So go ahead and do that now. And you should discover that the mean is 40 grams. So the average weight of an Oreo cookie is 40 grams. Okay, for part B, it says find the probability that the mass of an Oreo is no more than 3 grams from the mean. So if I'm looking at this visually again, I have my average now is 40, and I want to find the probability that the mass, so probability is the area under the curve, that the mass of the Oreo is no more than 3 grams from the mean. So I need to go 3 grams to the right of the mean and 3 grams to the left of the mean. So I'm trying to find the area of the curve, and that should be equally distributed, but my bell curve there was not drawn very well. So because it's the same number to the right and to the left of the mean. So I'm trying to find the area of that blue portion. So how can I do that? Well, now that I have my average and I have my standard deviation, I'm just going to go back to my normal CDF, right? I'm trying to figure out what the area under the curve is between two numbers, 37 and 43. So my normal CDF, 37 is my left bound, my lower bound, 43 is my upper bound, 40 is my average, and 1.5 is my standard deviation. So when I punch those numbers into my calculator, I write this down to show work, and then you should have gotten an answer of 0.9545. So roughly 95.5% of all Oreo cookies have a weight between 37 and 43 grams. Okay, let's look at part C. Part C says cookies are rejected if they weigh more or less than 3 grams from the mean. So these cookies over here in the green region are the ones that are rejected, according to that first sentence. Cookies are rejected if they weigh more, so more than or less than 3 grams from the mean. Find the probability that an Oreo cookie selected at random will be rejected. Well, that means that if this is the area in the blue part, this is the percentage of Oreos that will be passed, that will not be rejected. Therefore, you know your area under the entire curve is 1, so I'm just going to do 1 minus 0.9545, and so roughly 0.0455 of the cookies will be rejected. So roughly 4.5% of all cookies will be rejected. Now let's look at part D. Part D says, okay, how many cookies would you expect to be rejected if you had a sample of 10,000? So if there were 10,000 cookies, how many would you expect to be rejected if roughly 0.0455 of them, so 4.55% of them are rejected? Hopefully you're saying, I need to multiply those two numbers together. Right? So if there's 10,000 cookies, I'm going to multiply that by the percentage that are rejected. So 4.5% of 10,000 cookies is roughly 455 cookies. And if you had more decimal places, then you could put 455 point, whatever those values are. My calculator, I don't have it right now, so it's just 455 cookies. Okay, let's look at this part E. Part E says a package of 100 Oreo cookies passes inspection if no more than 10 cookies are rejected. Okay, let's think about that. 100 cookies. How many would we expect to be rejected on average for every 100? Well, hopefully you're saying about 4.55 cookies, right? So 4.5% of 100 is roughly 4.55 cookies for every 100. So a package of 100 Oreo cookies is going to pass inspection if no more than 10 are rejected. Well, are we expecting it to pass? Yes, we have a high probability that's going to pass based on what we know from part C. But how do we prove that, or how do we actually calculate the probability that a package passes inspection? So I have the probability or the average that it's going to be rejected. the probability that it's going to be rejected. So I'm either going to have rejection, success, or failure. I'm going to have success, it's going to pass, or failure, it's not going to pass. So my probability of it failing is 0.0455, and this says, or my probability of it rejecting is 0.0445, and this is saying no more than 10 cookies are rejected. So I have to go back to what we learned last lesson and use my binom CDF, right? No more than 10 means less than or equal to 10 cookies need to be rejected. Out of 100, there is a 0.0455 chance that any cookie will be rejected. And we are looking for that average to occur between 0 and 10 cookies, or what is the chance to have no more than 10 cookies rejected? So that's between 0 and 10. That's your binom CDF. Here's my probability that it will be rejected. It's caught between 0 and 10. I plug that into my calculator and I see I have a 99% chance that the package of 100 Oreo cookies will actually pass inspection. All right, have a moment and think about that. Go ask your teacher if you are confused. Finally, this last question, you might want to pause and do it on your own. If not, you can follow along with me, but otherwise pause and have a go at it on your own and then check your answers when you're done. Okay, example 4, it says a random variable x is normally distributed with an average mu. In the following diagram, the shaded region between 9 and mu represents 30% of the distribution. So 30% of the data lies between 9 and whatever the average is. So find the probability that x is actually less than 9. So we want to know what this area is right here. Well, remember that 50% of the data is to the left of the average and 50% of the data is to the right of the average. So if that's actually the case, then I'm going to take 50% and subtract the 30% and see that this green portion right here is equal to 0.2. For part B, it says the standard deviation of x, so we're talking about x, the standard deviation of x is 2.1. So if we know that, how do we find the value of m? Well, they're talking about the standard deviation. They're telling us what the standard deviation is. Okay, well, I'm stuck. I don't know what to do. I need to have some kind of z-score in order to help me figure that out, because I have a number, x, right? This is my x. I have a standard deviation here of 2.1. And if you look at your z-score formula, it's x minus the average divided by my standard deviation. I have my x, that's 9. I need to calculate my average. That's my unknown that I'm actually trying to solve for. And they told us the standard deviation is 2.1. Right, so for this value of x, we have a standard deviation, or for this, sorry, x is representing all of this data here, right? So this, whatever this distribution is representing, so it has a standard deviation 2.1. So how do I get a z-score? Because I can't find my average. That's my unknown. So how do I get a z-score? I have to use something that was given to me up here in this information to get my z-score. Well, the only thing that was given to me was this number 9, right? And what do I know now in relation to the number 9? I just said to the left of number 9, this is representing 20% of the data. And if we have a percentage in relation to a number, then we can use inverse norm to actually calculate what standard deviation that represents in the context of this problem. So 20% of the data, we can put it in the context of 0 to 1, not in the context of the problem, but we can figure out what the z-score is related to this. And so I would plug that into my calculator, inverse norm, 20% of the data and how it's associated with the number 9. So that would tell me that I would get a negative 0.84162. Okay, what does that mean? That means that the 9 is less than 1 standard deviation away. It's actually 0.84162 standard deviations away from the mean. So that is now your z-score. And you need to have a negative in front of there because it's to the left. So that has to be included when you are doing your calculation over here. Right? So make sure you're including that negative because it is to the left of the average. So do your cross multiplication, minus your 9, isolate your average or your mean, and you should get, in the end, you should do all the calculations on your own, but you should have gotten that your mean is equal to 10.767. All right, part C. Part C says the random variable y is normally distributed with mean lambda. So this little symbol here means lambda and standard deviation of 3.5. The events that x is greater than 9 and y is greater than 9 are independent, where the probability of x greater than 9 intersecting the probability of y greater than 9 is 0.4. So remember your test for independence means the probability of x greater than 9 times the probability of y greater than 9 is going to equal to 0.4. Okay, how is that helping me? Well, I don't know what y is. That's a whole separate graph and a whole different scenario, but I do know that x, we're talking about x up here in this graph. And so it says the event that x is greater than 9. Well, x being greater than 9 is here on over. Okay, well, what do we see here? We see that this shaded region is 30.3, and we know that to the right of the mean is 0.5. So the probability that x is greater than 9 is 0.3 plus 0.5, which is 0.8. So I know that this value right here is 0.8, and I can calculate the probability that y is greater than 9 because I now have everything except the probability of y greater than 9. So I'm going to divide by 0.8, divide by 0.8, divide by 0.8. So the probability that y is greater than 9 is equal to 1/2. Okay, so now we're talking about y. The probability that y is greater than 9 is 1/2. The probability is the area under the curve. If the area under the curve is 1/2 or 0.5, that means that 9 has to be the what for the normal distribution relative to the variable y? It has to be the average. So lambda, oops, I shouldn't have done an x there. Sorry, lambda should equal 9. Lambda is representing the average, therefore the average is equal to 9. Because the probability that y is greater than 9 is 50%, which means average has to be 9. Okay, finally our last one then, it says given that y is greater than 9, find the probability that y is less than 13. So given that y is greater than 9, okay, so now this is our average, this is our y value, so this is 9, then what is the probability that y, oops, sorry, I did greater than instead of less than, my bad, that y is less than 13. So given that y is greater than 9, well, given that y is greater than 9, that's the denominator. The denominator has to be 0.5. Then what is the probability that y is less than 13? Oh dear, how do I find that? So the only way to find the area under the curve from 13 and to the left is to use your calculator. What are you going to use for your calculator? You're going to have to use your normal CDF. But remember, it says find the probability that y is less than 13. So given that y is greater than 9, find y is less than 13. You need the intersection between 9, greater than 9, and less than 13. So you only need this average right here in between 9 and 13. So we're going to normal CDF this problem. So normal CDF, and you're going to go from 9, lower limit, 13, upper limit. Our average is 9, that's why there's another 9 here. And then our standard deviation is what? Remember, that was given to us down here in part C. So your standard deviation is 3.5. So when I calculate that, I get 0.373451. So that's the intersection of greater than 9 but less than 13. That goes in my numerator, divided by the probability of just greater than 9, which we said was 0.5. And when I calculate that, I get 0.7469. So that's my final answer. Given that y is greater than 9, find the probability of y is less than 13. So the probability that y is less than 13 is 0.7469. All right, it's a tough one. There's a lot of information here. Make sure you seek out your teacher, ask questions if you're not sure. That's it. Bye.